Okay, so let me quickly recap what we have discussed regarding hybrid ARQ with soft combining. So I was mentioning that hybrid ARQ is something where you want to do both forward error correction along with retransmissions whenever you see that FEC fails. So what we have is more than hybrid ARQ. We also do something called soft combining, where we try to use the previously unsuccessfully received symbols at the physical layer, and you try to combine them along with the retransmitted symbol with the hope that combinedly we can able to have better decoding of the entire set of symbols that are out there. So I will explain in today's class how soft combine is indeed achieved at the physical layer, whereas hybrid ARQ is the one that is done at the MAC layer. And eventually, if the things are not going good after certain retries, which is also configurable, you can discard the packet. It is up to the higher layer to figure it out whether you want to do it RLC if it is in AM mode, or you want to do it at TCP or quick if you have configured your applications to use one of those protocols at the transport layer. What we use is something called hybrid ARQ in asynchronous and adaptive mode. I hope all of you understood what I mean by adaptive, where based on the channel conditions, you decide how many resources to be allocated, what should be the MCS for the user, and all that. And other thing I was saying yesterday is about asynchronous ACKs and NACKs, where when you send the packet to the receiver, for example, if the base station is sending packet to the receiver, you can configure the receiver to send acknowledgements or negative acknowledgements at different time instances. That is what it means by asynchronous. Even in the uplink, when the handset is sending data to the base station can send acknowledgement to the handset at a different time instances. Whereas in the case of LTE, it was synchronous in uplink and asynchronous in downlink. That way, the acknowledgements in coming from base station to the opposite. Yeah, the acknowledgement coming from the base station to the user equipment will come after 3 millisecond kind of thing. That is not the case in the case of 5G, where we use a configuration setting where we can able to modify when you can expect acknowledgements or negative acknowledgement from the receiver in both downlink and uplink. Okay, so this is what I was showing you. I hope you are able to understand what I meant by here. Unlike 8 stop and wait processes in LTE, we are having 16 processes. That way we can able to send data 16 in parallel. Even though I'm using the word parallel, in a true sense, it is not parallel. So try to understand why I'm not saying they are not really parallel. So look at what is happening at the bottom. Let's assume that for convenience, each transport block is sent over a time interval of 1 millisecond. So if it is 16 parallel stop and wait processes, it is like at, let's say, if it is assumed that this is a time t equal to, G. Okay, I'll use it here, and this is t equal to 1. This is t equal to 2. Let's assume that these are the different scheduling time intervals or time instances. At time t equal to 0, we are taking one transport block, which is nothing but, so what is transport block? Can somebody tell me what is transport block? I was saying yesterday also, transport block is nothing but
the MAC frame.
Yeah, it is the combined or the aggregated MAC packet where you take the data from multiple logical channels and some control elements from MAC layer itself into a single or a combo packet kind of thing. So you can assume that transport block is nothing but a combined MAC packet by taking data from different logical channels. So where what I am showing here is at time t equal to 0, the MAC layer is sending one packet over the air. At time t equal to 1, it is sending another MAC packet. At time t equal to 2, it is sending another. So like that, we are configuring 16 such processes where if you look at any given time, we are not actually having 16 processes sending their transport blocks or MAC packets simultaneously. At any given time, we are only sending one of the transport block or one of the MAC packet because we have only one radio channel on which we can only share or we can only send one combined packet over the air. But what is the meaning of having 16 stop and wait processes? Like in this example, what you see is there are four processes that are configured at sender and receiver, where the sender and receiver can agree upon how many processes to be used for communication between them, and the data will be exchanged between them. Where, for example, if you look at process 0 between the base station and the handset, process 0 is used to exchange, let's say in this example, the packet 1. It is the responsibility of the process 0 to successfully receive the packet 1. If not, it is giving negative acknowledgement to the base station. Then the base station will retransmit the same packet again using the same process, but at a different time instance. So that is the example that you can see it here. If you look at time t equal to 1, you have sent packet 2, okay? And unfortunately, the decoding was failed. That means the CRC check is failed. So because of that, you got negative acknowledgement, the NAC. Upon receiving the negative acknowledgement, the we are sending the resending or retransmitting the packet 2. That means the MAC packet 2. Now this got retransmitted again using process 1. Is that clear what I'm saying? The entities that you maintain at the sender and receiver to retransmit a given packet is the same. Like that, we can have 16 such processes maintained. Rather than saying, "Oh, I have a sliding window of 16, I'm saying that we have 16 stop and wait processes, which are kind of decoupled from each other. Where if you see that the process 1 is trying to retransmit um, packet 2, but you can see that all other processes, in this case process 0, 2 and 3, they are able to successfully transmit whatever the packet that are coming, and they are processing other packet. If you look at process 0, initially it transmitted packet 1, after that it is processing packet 5, and the process 2 is transmitting 3, after that it is transmitting 6, whereas the process 1 has transmitted 1, unfortunately it has to retransmit the same packet again. So like that, we have independent processes who kind of coordinate with each other in terms of sending packets and getting positive or negative acknowledgements and doing the retransmissions wherever is required. So this is what I wanted to say. So is that clear to all of you? What I was trying to explain.
Sir, in this diagram we have four processes, right?
Yes.
So if we have 16 processes, then
Hmm.
like 16, all the 16 processes will send one packet each, and then process 0 will again get at the 17th time.
Yes, you are right. You are right.
Right. Okay.
Right.
So then how is this different from the vanilla stop and wait protocol that we use in the
No,
internet?
it is stop and wait only. There is nothing great about what I'm showing it. We are using very simple stop and wait, but rather than using one stop and wait, we are using multiple stop and wait.
Sir, but at least functionality wise, they seem to be doing the same thing, like whether it's in parallel or in the the vanilla case. So you said that so process one needs to retransmit packet two.
Mm.
So even in the normal sliding window case, if some packet needs to be retransmitted, the other packets can still be sent out, right, inside the window.
So you are
So
talking about selective repeat kind of situation,
yeah,
right?
yes, sir, correct.
Oh,
Yes, sir.
you are talking about comparing stop and wait with sliding window, is it?
Okay. I think I'm confusing it. Okay, fine. I got it, sir. I understood. Yeah.
So you are talking. So you are comparing one stop and wait versus multiple stop and wait. So what I'm saying is, in this example, let's look at the case. Say again, this is see what I'm trying to say is having multiple stop and wait processes is equivalent to having sliding window protocol.
Got it, sir. Understood. Yes, sir.
That's what I was saying, and also try to understand why we need to have more than one. So can somebody tell me what happens if I have only one stop and wait process? If I have only one, what is the thing that I will lose if you are having only one stop and wait process? Why I need to have more than one? So forget about 16 or 8. So what benefit I get, or what benefit I am getting by having more than one stop and wait?
Sir, I guess the same benefit we get with selective repeat.
Right. So what you are saying is in the selective repeat, we can selectively retransmit and while other things can keep going on.
Yes, sir.
Is that what you want to say?
Yes, I guess.
Okay. In other words, try to make it simpler. What happens in this illustration if I have only one stop and wait? What happens? If you are asked to redraw this picture with one stop and wait process, what will be, how it will look like?
So it will have to wait for that packet to be acknowledged or not acknowledged.
Yeah, let's look at from the beginning. First, we have the packet one. That means transport block one. You transmitted, right? At t equal to 0, you transmitted transport block one. So this is the example that I'm showing. This is sent. Now, the base station, can it send a second transport block or second MAC packet at time t equal to 1?
I don't think so, sir, because it doesn't have the act at that
Yeah.
point.
So, Suranjan, what you are trying to say that is, it is going to take non-negligible amount of the time for the receiver to process the packet, check whether the CRC is pass or fail, and sending positive or negative acknowledgement, right?
Yes, sir. Yes, sir. So basically, here we are getting the same gains that we get when we do pipelining.
Yes, yes. So rather than using sliding window, we are using multiple stop and wait. That's what is happening here. So if you look at here, the picture, after sending packet one, there is certain propagation delay. It is could be in a few microseconds or tens of microseconds depending on the distance. Then the receiver, whichever receiving the packet, it has to decode the packet and it has to check the CRC check. Then it has to contact the MAC scheduler to send acknowledgement. It could be positive or negative. It and all this could take some amount of the time. But by the time, as you see, by the time you transmitted this packet at this time instant, as you see clearly, the transmitter is ready. In this case, the base station is ready to send another MAC packet. But unfortunately, if you are using stop and wait, you all of you know, right? You send a packet and you wait till you get the acknowledgement. But as you see here, there is some amount of the time that is involved. So this is greater than 0. All of you agree with me. Hmm? So because of that, we are kind of holding the sender. Sender is kind of ready to send multiple packets. By having one stop and wait, we are kind of wasting the channel resources when you have large bandwidth delay product kind of thing. So that we can address by using multiple stop and wait or by using sliding window. But at the MAC layer, we are using multiple stop and wait. At RLC layer, we are using sliding window protocol, as you have seen in the previous classes. So, and another thing that I also wanted to highlight is the demultiplexing is happening. If you look at for packet 1, after that 3, 4, 5, and later the demultiplexing or kind of a successful decoding of packet 2 happen. But the packet 3, 4, and 5 need not be kept in the receiver buffer at the receiver side. They can be directly transmitted to the higher layer. And if at all you need any kind of in sequence delivery, you can configure at the PTCP layer. So like that, we don't need to have bigger amount of buffers for ensuring the reliable delivery or the in sequence delivery by using this kind of approach, which is kind of different from what was done in the case of LT. Shall I move on, or anybody having any other queries on this slide?
Here, if we are having, suppose 8 processes, is process 0 to process 7, and if the first packet had some error or something, then only after the packets 1, 2, 3, and 8 are transmitted, then this packet 1 can be retransmitted.
No, 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 not like that. It is not at all like that. Okay, I think it is a good question, Ranjita. So, so look at here. In this case, what happened? It all depends on when you receive the acknowledgement. In this case, negative acknowledgements. If you receive negative acknowledgements quickly, let's say you are talking an example where there are 8 processes, right? So let's assume that we have 8 processes, and even look at this example itself. So in this example itself, if there are no failures, you would have sent packet and the packet 1, 2, 3, 4, 5, 6, 7, and 8, right? That's what you might have transmitted. As soon as you have received negative acknowledgement, in this case, as soon as you receive negative acknowledgement, in this particular time slot here, you are retransmitting the packet 2 using the process 1. So this is transmitted using process 1. So what is the timestamp? If you look at, I think it is, I'm going with zeros, I think. So if you look at that way, it is T0, T1, T2, T3, T4, T5. Yeah. At time T equal 5 itself, you are retransmitting. That means you can actually decide which of the processes can transmit their packet in the next scheduling interval. It need not be sequential.
Okay.
But what you are kind of doing is, rather than waiting for that to give acknowledgement, you are kind of scheduling whoever is readily available. That's what you are doing it. But as soon as you know that there is a negative acknowledgement, to depending on the case, you can decide. For example, let's say you got negative acknowledgement for this packet 2, but you decided that this is low priority. Then what you can do, you need not to be doing at time t equal to 5, maybe you can delay to t equal to 10 as well. It's all up to the scheduler to decide when when it can do the retransmissions. In other words, what I'm trying to say, all these are highly configurable, reconfigurable, and adaptable. And so that way you can able to address all different application and their requirements.
Okay, so these processes would be one by one taking the packet from the RLC buffer, sir.
Yes, yes.
Okay.
No, no, not from RLC buffer. They take the MAC packet, which is composed of data from multiple RLC buffer. So transport block is nothing but your MAC packet.
Okay. Okay, so after the transport block is constructed, these processes come into picture.
Yes, yes. I think it is there, right? If you look at, I think I don't have, okay. I think, yeah, this is the one. So look at this one. Here we are composing one transport block, which is nothing but multiple MAC packets, which are nothing but data from the RLC buffers. So this could be from one, like this could be from one logical channel. This could be from another logical channel. From another logical channel. And these are the one related to the DCA and other thing, the control information. Okay. So all of them are kept together to create one jumbo MAC packet. So which we are calling it as transport block.
So the Max scheduler will take care of these creating these processes and then sending the packets.
No, no, not that. The MAC should see if you look at the thing. Look at
So
the
where
scheduler.
will this processes come in, sir?
Yeah. So the processes come here in this block.
Okay.
And what the multiplexing of different logical channels happens in this block. In other words, here we have the transport block, okay? And like that, you have transport block 0, 1, 2, and other thing. and they are fed as input to the hybrid ARQ transmission. So you decide, let's say you decided to have 8 processes or 16 processes or whatever it is. These are configurable. Then these processes take the data from the transport blocks, which are nothing but MAC packets, and send it using uplink shared channel. If it is uplink, it is downlink, they use downlink shared channel. In this case, it is by the base station.
Okay, sir. Yeah, I got it. Yes.
Sir, that means that the date when the data comes, the data is then multiplexed into RLC and then made Mac frames are made out of it, and then we do something like multi-processing or multi-threading, and each of the threads or processes take care of one of the frames and starts transmitting it.
So you are talking about hybrid ARQ processes, right?
Yes, yes, yes.
Yeah, you are.
Here is said that
Mm.
processes are coming and like transmitting it one by one.
Yes, yes. So what? So this is the MAC layer. We have one instance of the MAC layer, okay,
Right.
which can manage one or multiple cells at a given cell site. And here I'm saying that you can have up to 16 processes. Yeah, you can have. I can have one process inside. I can have 16 threads, which can take the data from these different transport block and send it using stop and wait protocol.
Right, right, sir.
Yeah.
Got
Again,
it.
all these are important. What I'm trying to emphasize here is the project, term project also. If you look at most of the things that I am asking you are related to the scheduling. So you should have good knowledge of how the scheduler is working in NR, and more importantly, how it is actually implemented in NS3. So we can have conceptually these are how the scheduling works. But at the implementation side, you can actually have multiple choices in terms of the how much buffer that you should have and how you should be sharing a kind of different logical channels. How do you want to do the prioritization? What kind of scheduling algorithm that you want to use? Okay, all those are highly configurable. Depending on that, your results will change quite dramatically. So try to understand this MAC layer, because MAC is the kind of the brain which kind of controls who should be served at what rate. Hmm? Okay, so let me move on. Okay, I guess this example doesn't require any repetition. Okay, can somebody tell me before I move on? So what is the disadvantage with what I was showing here, and why we need code block group level retransmissions? What benefit you get?
So to pinpoint where the error is, if there is error.
We can actually design three different schemes. What is the first one? Retransmit entire block, transport block, okay? And what I'm showing in this slide is the retransmit code block group. And what is the middle one? Can somebody tell me what is the middle one?
So maybe something like go back and where we transmit from the packet which was corrupted and till the end. I mean the CBG that was corrupted, and like if CBG 2 was corrupted, we retransmit CBG 2 and CBG 3.
No, I think you have to distinguish. So there are three terms here. One is the transport block, other one is the code block, other one is code block group. So did you guys understand how these three are related with each other? Hmm?
Yes, sir.
So
Last difference.
tell me what is this? How these two are related? First two.
Okay, so the transport block is the entire block and having only one CRC or
Hmm.
like whatever HARQ, like that FAC and things like that. And if we are sending it in one go, then if some error is happening, we don't know exactly where that error is, and we may have to transmit the entire transport block. So that's what we are doing is we are breaking the transport block into small chunks and attaching CRC to each of those chunks and then sending it, so that if some error is happening, we can pinpoint exactly where it is and resend that exact transfer CB code block. And in transport block group is that we are grouping some of the code blocks to reduce the that pinpoint accuracy, so that we don't have to transmit that many CRCs.
You are right, Suranjan. Did you guys understand what he said? The difference between the second and the third one. This is the first one, this is the second one, this is the third one. Same thing I'm showing it here as well. So out of these three, can somebody tell me which one is more efficient?
So efficient, we can say that, like if we say efficiency in terms of how much data, how much actual useful data that we are sending, then transport block is the most efficient because less CRC, less data transmitting.
But again, you know, right? What if things go bad? Then you end up retransmitting entire thing, right? So you assume
Yes.
that channel is inherently lossy and it is not possible for you to successfully transmit everything without the cost of adding some FAC and CRC bits. In a such a
Then the second one.
yeah. See, if you look at the second one, that is the optimal one. Do you guys agree with me or not? Second one is optimal in the sense if I divide my transport block into 100 code blocks, and at the receiver side, I check which code block is corrupted or not successfully received. I will ask the sender to retransmit only that code block. That way it is quite efficient if you ignore the signaling overhead or the control overhead. But unfortunately, the way it works out is this way. Let's assume that, okay, maybe I should, let me use small animation. So let's take this example. Okay, take the example of one transport block divided into 100. Okay, why 100? It is too big to visualize. Okay, 10 code blocks. So the way it works out is this way. It could be G node B and this could be UB and even another way also you can think of. And where you are transmitting one transport block, which is nothing but a collection of 10 code blocks. And what user does is this way. It has to give acknowledgement, right? The acknowledgement is nothing but a bitmap. So what is this basically means? Okay, okay, it all depends on what you treat zero. Okay, basically you can assume either way. Like in this case, if I interpret zero as success and one as failed, in this case, I'm informing the base station that the second code block is the one that got lost or not successfully decoded. So you please retransmit. In this case, what happens? Sender will retransmit transport block, but rather than sending all 10 of them, it will be sending the code block. Okay, if we start with 1 to 10, so this comes out to be code block 2. So that's how things are working here. But what I'm trying to say, the problem with CV level retransmission is the acknowledgement size grows. It is a function of the number of code blocks. The ACK size or the signaling overhead increases with increase in the number of code blocks. If you want to somehow cut down the signaling overhead, the option is grouping the code blocks into code block groups where you can take, let's say at least 2 of them together. In that case, by doing it grouping, so can somebody tell me how much is the reduction in my signaling overhead compared to here?
By half.
So I am able to reduce my signaling overhead by half. because here if you require 10 bits, here I can manage only with 5 bits. Of course, uh, yes, you may be right. You are unnecessarily retransmitting one of the things in case one of the code block is successfully received, other one is unsuccessfully received. But this is all done to make the entire protocol not becoming so complex and leading to all sorts of cases where the signal overhead becomes too prohibitive to even think of designing the system. So it is a kind of a trade-off. Ideally speaking, yes, Suranjan, you are also right. If the errors are very, very few, yes, don't do all these grouping, segmentation into code blocks and further grouping some of them and all that. But in all practical case, you have to be doing something between these two. So that way, this is what practically applied. So, sorry, not this one, the last one, yeah. Retransmitting at the code block group level.
So in that animation, if there were two 1 bits,
Mm.
then the second TV second transport block will be sending two code blocks, right? Together or single.
No, no. Oh, okay. I don't have that animation. I guess it gets lost by the time I come out. So what you are saying is like take this example itself. Take this one. So what you are saying is let's call it as one and this is the second one. So what your example is both one and two are lost in this code block group. That's what you are talking about.
No, no. In the last line, like in case of CB, not
Okay.
CBG.
Oh, you are not talking about. Okay. So let's assume that. Okay. Let's look at the bottom one. So where I have one, two, three, four, five, six. Okay. Now tell me.
So if say 2 and 5 are corrupted,
Mm-hmm.
so in the retransmission, we send 2 and 5 together or 2 and 5 separate transmissions.
No, no, no. Again, you will be sending everything as a transport block, right? At the end of the day, again, if I think maybe confusing whether it is this one. In other words, look at the case one, case two, and case three. At the end of the day, I'm sending everything as a transport block. Finally, I take code block groups together, or I take code blocks together and create a transport block.
Okay, okay.
So what I'm trying to say that what you will be sending at the end of the day is the transport block. One thing is I can have a transport block with a simple CRC. That is one option. That is, let's say, case one. Or I can create my transport block if I'm doing the CB level thing as collection of code blocks to where if you open any of them, it will actually look a part of the data plus its CRC. So this is the case. And if I do the opposite one, so if I draw another animation here, so this is the transport block, which is composed of code block groups, then how it will look like? And okay, and if I open it, any of this, so I will have CB1 with its CRC and CB2 it's with the CRC. In all these cases, what I'm transmitting is a transport block. But what is important to note down is the case where the example that you are talking about. In a given transport block, the lost packets are 2 and 3. And assume that it is composed of 1 to 5. Out of that, three of them are successfully received and two of them are lost. So when you are retransmitting, the retransmitted transport block contains the second one and the third one. It can contain new code blocks as well, which are coming from again higher layer.
Okay, okay. Got it.
So it's not that I'm going to waste my channel resources by keeping the rest of the thing as blank. Why you will do that? You don't want to do that, right?
Yes, sir. Yeah, got it.
Okay, any other doubts? Looks like I'm taking more time, but let's see. Okay, I think this is one of the example showing how it is indeed done, where if you take the code block group level transmissions, look at the base station is sending a transport block, let's say TB1, which is comprising of two code block groups, where the size of each group is two code blocks. And it is saying that this particular transport block is corresponding to the process one, HARQ process one. And also look at this one. In PDCCH, as part of downlink control information, the base station is informing to the handset when it is expecting the acknowledgement, whether it is a positive acknowledgement or negative. That information is also sent along with the transport block or inside the transport block. If you recall, transport block not only contains the user data, it also contains the control elements. If you recall, control elements. So one of the control element that it carries is the DCI, which it says all this information about which HARQ process the data is going into and when the acknowledgement should be coming from the handset to the base station uplink. Then after receiving the data, handset has to wait till that particular time slot arrives, and in this case it is saying that I'm unable to successfully, like this is the one that example we are talking about is lost. That means code block group 0 is lost or kind of not received successfully. For that reason, it is giving negative acknowledgement for that particular one or physical uplink control channel. Now the base station see what it's doing. So in this example, again, in this cartoon, I'm showing the case of a transport block, which is only containing the retransmitted code block 0, but it actually can contain additional data as well. Additional data. Okay, otherwise we are kind of wasting a lot of resources. Okay, and also look at what is being conveyed in addition to this. In this case, it is saying that okay, the data that is coming now, again, it is for the same HARQ process, that process one, and the data that it is sending now is not the new data. New data indication flag is set to false. That means it is a retransmitted data. So now, because it is not new data, the handset after receiving this packet, it can think of using it for soft combining. So the objective of the soft combining is, like in this case, first time when this packet was received, even though it is unsuccessfully received, it is keeping it in a buffer. And now the retransmitted one is coming. In case the retransmitted one is also failed, the CRC check and other thing, you also put that in the buffer. And you combine this as part of the soft combining process and try to decode and see whether it is a success or failure. But that is what the new data indication field is. And look at, I also was telling earlier, we have something called code block group transmission information, which is nothing about bitmap. In this case, it is saying that like, because there are two code block groups, so we need only 2 bits. Like here, the indication of 1, it means that code block 0 is getting retransmitted. And we are not retransmitting for code block group 1. So that means we are not retransmitting code block 1. So this is not getting retransmitted. We are retransmitting for this. Also, we have another flag, which is, as the name says, CBG flush indicator, where the sender can also indicate to the receiver whether the receiver can flush its buffers, or it can use the new transmission and combine this with what is there in the buffer to be able to successfully decode. All that also can be sent as part of the control signal in DCA. Let us look at the hybrid ARQ and soft combining in a big picture here. So let me try to explain what is happening at the physical layer after you create a transport block. So the information bits that you see it here, it is nothing but the transport block that is given by the MAC layer to the physical layer. So look at what physical layer is doing. It is first adding CRC check. And at the receiver, so ignore the below blocks that you see it here. So at the receiver, what we do is you check the error detection is what you are doing it. And if it is success, well and good. If it is not success, you have to send negative acknowledgements. So far, what I was describing in all these slides, what I was describing all these slides as ARQ part is this part. I was describing you what is happening as part of these two peer entities at the transmitter and receiver. Does that make sense? You are taking a transport block and adding CRC and sending it down the line, down the stack and over the air. At the receiver, again, once it reaches the error detection module, you check the CRC check, and if it is okay, it is fine. Otherwise, you send negative acknowledgement to the sender. Sender will retransmit the transport block, depending on whether it is a block level retransmission or whether it is a code block group level retransmission. It is all highly configurable. But I didn't describe what is happening below the thing. So that's what I'm going to talk now. Let's look at what is happening down the line. So after you add the CRC check, let's assume that we are not doing segmentation of the transfer block into code blocks and other thing. But again, the discussion will be valid even in that case. So look at what is happening. We have the transport block combined with CRC that is given to the coding layer. So here we use something called a low density parity check. It is the coding scheme that has been decided for 5G, whereas in 4G we use something called turbo codes. These are error correction codes. So CRC and all what you use in the MAC layer and here at the CRC attachment, these are only error detection codes. They check the CRC using some CRC polynomial and they say yes or no, but they cannot be used to detect bit errors. To further improve the transmission success, what we do is doing the channel coding. In the channel coding, you take the data and you add the forward error correction. You add lots of redundancy bits are also called as parity bits. And then you send it down the stack. So what you see is the coding. In some of the cases, what happens is as part of the coding, the number of bits that are added, which are called redundancy bits or parity bits, they could be 2-3 times higher than the original bits. Let's say if the input, let's say if the size of this is n, the output that you get out of this could be 2n or even 3n or even 4n. That means, let's say you want to send 0, 0. So what we are doing is rather than sending 0, 0, if it is 2n, you are sending, let's say 0, 1, 0, 1. So this is the original data. And this is the original data combined with parity bits or redundancy bits. Okay? The idea here is by adding these parity bits, it becomes easier for the receiver to correct some of the bit errors rather than asking sender to retransmit. But if you look at the coding rate of this particular thing, the coding rate, if you look at, is defined as something like how many bits that you want to transmit, in this case n, but how many bits actually transmitted over the air. If it is 2n, the coding rate is 1/2. And if it is 4n, it is n/4n. The coding rate is even lower. So that means if you start adding more and more parity or redundancy bits, your ability to successfully correct most of the bit errors will increase. But you are actually sending 3 bits in this example. In the case this example, for sending 1 bit, you are adding 3 parity bits. So that way redundancy is kind of quite high. It is good, but at the same time, rather than sending information bits or the user bits coming from higher layer, we are kind of trying to do a lot of redundancy bits. So that is should be used only when the channel is highly lossy or when your application demands ultra high reliability like URLC application. Then to as I was talking about, in all these cases, the channel coding schemes they really emit or kind of give out lots of redundancy bits. To able to make sure that the overhead of the redundancy bit is not significant, we do something called rate matching. Rate matching does something called puncturing. As the name says, puncturing. What you do is you delete or you remove some of the redundancy bit. Redundancy bits or the parity bits. That way, the coding rate won't be so bad or so low. So an example could be originally we have n bits, and after channel coding you got it as 4n bits, but after rate matching you decided that to send only 2n bits. So at this stage the coding rate is 1 over 4, but finally if you look at the coding rate is 1 over 2. So that way you kind of improve the coding rate by removing some of the redundancy bits. So it should be interesting to note down why we are doing this puncturing. The logic behind puncturing is first time, like as you see here, we have original n bits. Rather than sending n, we are sending 4n by adding 3n redundancy or parity bits. But you are not transmitting all 4n bits. Instead, we transmitted, let's say, the original n bits plus n redundancy, n parity bits. So these are received at the receiver. But for whatever the reason, assume that this packet is not successfully decoded. Then the sender will retransmit again n bits plus another set of n parity bits. So this thing can be combined with this as part of something called soft decision combining. Where when you are retransmitting the punctured bits or the punctured parity bits, so that at different times, that means you have lot of redundancy bits, but you are kind of checking whether channel is so bad or not. So initially you try transmitting only a subset of redundancy bits, and if everything is good, you kind of save a lot of overhead because you are now sending all parity bits. But if it is not the case, you ask the sender, why don't you retransmit even other set of punctured bits? So like that, only when the channel is highly lossy, then you end up actually going from coding rate of 1 by 2 to the 1 by 4. So that way we are kind of doing things adaptively. Channel is good, yes, I can achieve 1 by 2 coding rate. The channel is bad, it will go to 1 by 3, finally it end up going to 1 by 4. That was the original thing that we have actually in mind before you started doing the puncturing. So let me, okay, I think I have an example also. I have anyway explained what is puncturing, but this is an example for you to understand. These are the original bits. I have 101. These are my original bits. It is also called in the terminology of LDPC codes as systematic codes, systematic bits. So look at, I have 3 bits. So these are my parity bits. To send 3 bits, we are actually adding 3 more bits. Finally, we have 6 bits. So that way, if you look at the coding rate, it is 3 by 6, which is equal to 1 by 2. But it is too much, right? And the coding rate is, for every bit, we are adding 1 redundant bit. So we do something called puncturing, as you see. In this case, we are defining what is the puncturing pattern. It says that you are puncturing this bit, you are puncturing this bit. So that way, you added 1, 1, and 0. Out of that, one of the one you are not actually transmitting, one of the parity bit. Another parity bit also you are not transmitting. The third parity bit you are actually transmitting. If you look at the coding rate, so you have the original 3 bits and you are sending these 3 bits along with one parity bit. That way the coding rate has improved from 1 over 2 to 1 over 4. Oh, sorry, 3 over 4. And let's look at the coding rate. in the context of 5G. So I was showing you these tables. Okay, sorry, I didn't show you this table, but I was telling you about based on the channel quality, the transmitter will decide what should be the modulation and coding scheme as part of adaptive modulation and coding strategy. That's what I was telling, but I didn't show you how exactly these things are selected. So let's look at the case. For timing, assume that depending on channel quality, it could be depending on the channel quality, SNR or SNR, you did the mapping to MCS. So let's assume that that has been already taken care. Then yeah, look at here, this example, maybe there are multiple things to look at. I will show you the things with respect to one of the MCS. Let's assume that we have these set of MCS which are highlighted 10 to 16. If you look at, all of them are having same modulation order. That means for all, in all these cases, we are using something called modulation order 4, means we are talking about using 2 power 4, that is 16 QAM. Whereas the first one is, what is this one? This is QPSK.
The normal QAM.
Yeah, this is
Okay.
QPSK.
Okay.
And this guy is the 64 QAM. And fine, okay, I think this table is actually called 60, oops. This table is called 64 QAM table, okay? Where is that? Yeah, this is called, yeah. This is called 64 QAM table because the maximum thing that you can see in this table is the 64 QAM. And also you see, we have a couple of things reserved. These are used for retransmissions. And you have one such MCS defined for each of the modulation scheme, like for QPSK 16 QAM and also for 64 QAM. And we have another table which is called 256 QAM table. So this is used when the channel conditions are good. Oops, I think my system is slow. Yeah, so this is used when the channel conditions are good. If you look at very carefully, we are also using packing 8 bits in a given symbol, that is nothing but 256 QAM. Plus we have one more table that is used for URLLC. It is having low spectral efficiency. The reason why I'm saying it is having low spectral efficiency is here the coding rate is extremely low, and we'll be using also different modulation order starting from QPSK to 64 QAM, but the number of bits that you keep, the information bits or the systematic bits, are quite low compared to the parity bits that you pack in a given transmission. That's the reason why the spectral efficiency is very low. So let me come back and show you what I wanted to highlight here. So let's look at the figure where I'm showing you 10 to 16 MCS. There are 16, these are different MCS which are having 16 QAM as a modulation scheme, but they differ in terms of the coding scheme. So again, I'm saying we use something called low density parity codes. These are having a very good efficiency in terms of successfully decoding the bit rate, so in transmitted bits and other things. But what you see it here is depending on how the channel and all the cases, you decide how many number of information bits that you wanted to pack. So how it works out is something like this. What you see is the target code rate. Like look at here, this part. So, and look at this value. So what is the meaning of this is that R into 1024 equal to 340. So that means your rate, the coding rate equal to 340 information bits over 1024 transmitted bits. That way, approximately if you look at 700 bits here are the parity bits, only 300 bits are the information bits with a very high amount of redundancy you are transmitting. But with for the same modulation order, that means for 16 QAM, we can also think of packing 658 information bits in a interval of in a block of 1024 bits. So here for every bit there is only one redundant bit kind of thing approximately. So like that we can decide for given modulation order what could be the coding rate, and the SNR is even lower, you can fall down to even lower modulation orders, and also depending on the QoS requirement of the applications, you also decide what coding rate to choose. For example, you are talking about URLLC, maybe start thinking about like ideally you should be using the third table. Now come back and see here. Like, okay, maybe I will show you the same example. Okay. Like here you are packing 30 bits over 1024 bits with QPSK. Okay, that is what you are doing it here. Oops. Whereas here, if you look at this case, you are actually packing even in the starting of the table. Oops, what is happening? Even in the starting of the table, you are packing 120 bits in the interval. And when the channel conditions are bad, okay, here also you see it is starting at 120. There's a slight difference as you see across the table from the starting values in the coding rate and where they are ending and other things. So table 1 is used for the channel when the channel quality is not so great, where you go from QPSK to 64 QAM. Table 2 is used when the channel quality is good, where again you go from QPSK to 16 QAM along with 256 QAM. And there you can get better spectral efficiency because you are able to put more and more bits in a given code block that you are transmitting over the air. And the third table is used for high reliable applications like URLLC use cases. Yeah, so that's the relation between what I'm showing here. So where I'm talking about adding some code bits, and after that, like look at here, this example again, take this case again, where you take the 16 QAM and you decided to send with this particular coding rate. But what the puncturing says is, you don't need to really send 1024 bits to represent 340. You rather than send a subset of that. So by doing that, we get R dash, so which is equal to 340, and this value is less than 1024. So because of that, R dash will be greater than R. Does that make sense what I'm trying to show here? So first what we are doing is, depending on the channel quality, that means using SNR or SNR, you are deciding what should be the modulation order and what should be the coding rate. And since we have the soft combining feature and you wanted to take the risk of some packets getting lost and they could be retransmitted using ARQ mechanism, you are doing the puncturing process where you can kind of omitting some of the parity bits, and if it is unsuccessful, then only you retransmit these parity bits and use a process called soft combining to be able to successfully decode the thing to the extent possible. So there are actually two kinds of soft combining that are there in the literature. The first one is a very simple one, which is called chase combining, where the puncturing pattern is same for the original packet and for the retransmitted packet. So look at this example. The first transmission is having, I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah, 12, yeah. So there are 12 original bits And if you actually look at the coding rate, so can somebody tell me what is the coding rate here? If you don't do the puncturing, if you transmit all the systematic bits and the parity bits, so what is my coding rate?
12 by 36.
So this is 1/3. And what you do as part of puncturing is you are only sending only 3 bits out of 24 redundant or parity bits. So what is my R dash?
12 by 15.
So you see a huge jump in the coding rate, right? So that's what you do as part of the puncturing. And this example is where the retransmitted packet and the original packet will have the same bits transmitted in all the attempts that you make. So this is a combined packet. In case if the first one is fail, that means CRC fail. And if the second one also has the CRC fail, then what you do? You take this and you take this as part of soft combining and then try to see whether you can able to make use of this. It is as similar to a given packet is transmitted from 2 base stations. Let's say I have the user equipment. I'm sending the packet over this base station and I'm sending the packet over the same base station. And the user equipment can try to use these 2 packets in case one of them, if none of them successfully received as part of the soft combining process. But here, rather than using 2 base stations as part of dual connectivity, what we are doing is we are retransmitting using NAC that is coming from the receiver. The second one is called incremental redundancy, which is also called IR, which is very interesting one. So look at the animation to understand. The puncturing pattern varies from the original one to the retransmitted one. And interestingly, if you look at the retransmitted one is not at all having any original bits. The retransmitted one is having more of the parity bits. And if you look at the coding rate is the same here. Okay, I think here the coding rate is 12 over 15. I think it is, okay, how do you say that? You're transmitting, I think you're transmitting here 16, right? Here 12 bits, and along with that you are transmitting, and here you are not at all transmitting the information bits. What you are transmitting is, I think the coding rate we cannot define directly for this. But if you look at after combining, you not only got the systematic bits, you got more or less almost all the parity bits which are there before you doing any kind of puncturing. That way the probability of successfully decoding this combined packet is higher than any of the individual ones that you can see it here. And how it applied in 5G, yeah, let's look at here again. First we have the transport block at the top, and then you can add the CRC. Then this is the transport block with the CRC. Then if we are talking about channel coding, in this case I'm talking about LDPC coding. So first what you see is the chase combining, where the puncturing pattern is the same. So you transmit, and if it is not successful, you retransmit the same thing again. And if it is not successful, you transmit the same thing again, you retransmit the same thing again. And if you look at the energy, that means the symbol that you receive and all the combined energy of them, if it is EV, and it is 2 times EV, and it is 3 times EV, and it is N times if it is Nth retransmission. So by having higher combined energy, your ability to successfully decode and all will increase. That is if you use chase combining. If you look at the bottom illustration, that is for incremental redundancy. Look at the picture. So this is my channel coded bits. Okay. After doing the channel coding using LDPC. So this is my original data along with my parity bits. Look at how we are transmitting. So this example is the case where you are transmitting only 1/3 of this, 1/3 of this packet here. And another 1/3, if the first 1/3 is not resulting in successful transmission of the transport block. And even if the second transmission also is not helping, even after soft combining, you transmit the third part of the original LDPC code that you generated. So that way, if you look at, originally you received this part and this you are not even transmitted. Second case, what you are doing is you are transmitting this part of the original LDPC code, and in the third attempt, so this that. So for that reason, if you look at in this illustration, you specify something called redundancy version, because in 5G we use the incremental redundancy, we are not using chase combining. So the redundancy version, whether it is the first one or the second one or the third one, that you have to specify as a process called rate matching. Rate matching is nothing but you identify what is the redundancy version and accordingly you do the puncturing. So rate matching, you decide what to puncture based on the redundancy version. Then you transmit that one. If it is not successful, then you send the other item, other one. So that way, if you look at the coding rate, because you are transmitting only 1/3, the coding rate is 3R. But if it is not helping, the coding rate reduces. And in the extreme case, only the coding rate comes to R. But that is not the case when you talk about chase combining. It has the coding rate R all the time. Again, I'm showing the same example. Try to look at what is happening at the physical layer of the transport block. It does a CRC check, and if needed, it also does the code block level segmentation and also code block level grouping to be able to easily manage the retransmissions. Then it does the channel coding using LDPC. Because the coding is introducing too many parity bits, we do something called rate matching using incremental redundancy version of the soft combining, where you do certain kind of puncturing and send it, the punctured code word, to the modulation. And if it is depending on what modulation, let's say if it is 16 gram, then it will take 4 bits and puts in one symbol, where these 4 bits could be combination of information bits and the parity bits. And at the receiver, if it is everything goes well, it is fine. But if not, whatever the packet that has unsuccessfully received, it is kept in a separate buffer. And as part of the soft combining, it will try to combine with the retransmission version and send it. For the receiver, for the sender to retransmit, we have to wait all the time, all the way till the CRC check. Only after CRC failure, we send the NAC. Then we again, sender will retransmit, this time with a different redundancy version.
Sir, why are we doing the CRC check at the end? Why can't we do it just after reception?
After reception. Which reception? Okay, at the physical layer.
Yes,
No, sorry.
in the receiver.
The entire thing is the physical layer here, okay? The whole thing is the physical layer. So when I say reception, it is the reception of the energy. See, so far what I'm talking about here is, once you receive the energy, the received energy is the one that you actually using as part of the soft combining process. It is all done at the physical layer. Only after that. So all these are the things that are the symbol level. Only after demodulation, you have the symbols that are converted into bits. You can check CRC only on the bit, not on the symbol. So Suranjan, do you agree with me? So
Right.
symbols are nothing but radiation. You cannot check whether the CRC is success or not. You have to wait till you get the bits. But here, before you do the CRC check, you do the forward error correction. First, you do the forward error correction. In spite of doing forward error correction, if your CRC is failing, it means that your FEC is not helping, and you have to ask the sender to retransmit by using ARQ process. That's the reason why it is a combination of ARQ, FEC, and soft combining.
Right, sir. Yeah, got it.
Okay, let me show you again where all these 3 things play a role in this physical layer process. So can somebody tell me which are the blocks that do ARQ aspects here? Here I have entities, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So tell me which blocks or which modules that you see it here out of 10 handle ARQ job. No, it's not clear.
The number 1 and 10, I think.
So what about others? Do you agree with what Suranjan said, or do you think something different than what he said? What he's saying that we do the ARQ. Here we are talking about what kind of ARQ?
The HAR.
Yeah.
Stop and wait, right?
Yes.
Here we are using stop and wait ARQ. So which are the modules that correspond to stop and wait ARQ in this physical layer blocks that you see? Somebody is saying no. So yes, this is the one that is corresponding to ARQ. Okay. So can somebody else other than Suranjan tell me which blocks corresponds to FEC?
Coding.
Coding. Okay. Anything else other than coding? You are right, coding, but not only the coding, this guy also, right? Even the error correction also.
Yes, sir.
So both of them do the FEC part. One case, sender is adding the parity bits. The receiver is using the parity bit to able to correct the bit errors in the transmission. And what about the rate matching? Rate matching is a kind of to reduce or improve the coding rate. Or you can also say that to reduce the redundancy. Okay. And then we have the modulation anyway, so that doesn't come. And yeah, so anyway, you can see it here, the soft combining. So that is responsible for soft combining. It is not shown, but you can also say that the RV that you are giving as input to the rate matching is also part of soft combining, because as I was mentioning, we are using the IR. So that way you can say that both these two modules do the soft combining. So like that, we have different blocks in the physical layer stack which take care of forward error correction. If it is not working, we ask sender to retransmit by using stop and wait process. But before even you do FEC, you do something called soft combining, which is trying to make sure that FEC will be successful to the extent possible. So finally, I have one more slide, which is a kind of thing what I covered when I was talking about RLC AM mode. So if you look at the hybrid ARQ, it is not completely reliable. One of the reasons why it is not completely reliable is that there is no error protection for ACKs and NACs that are coming from receiver to the sender. So what is the meaning of this? Look at here. We have this NAC packet, right? So there is no error protection for this, because it is sent on PUCCH. It is not sent on physical uplink control channel, sorry, physical uplink shield channel. So there is no error protection when you are sending NACs. So what could go wrong? Let's say you take the case where in this example itself, where the code block group 0 is the one that is not successfully received by the receiver, and the receiver is sending, in this case handset, is sending negative acknowledgement to the base station. And I don't know whether I told you this point or not. This ACK or NAC is just one bit, just a one bit flag. So because of the bit errors, what if this bit get flipped? So what would happen? What would the base station think when the handset is sending NAC? and we have this bit error which flipped the bit from 1 to 0.
So can you repeat that? Like I lost signal, I could not hear the last part.
Okay, so what I'm asking is, in this example, the base station has sent two code block groups. Out of that, one of them is having bit errors. Because of that, handset is asking the base station to retransmit by sending a negative acknowledgement. Here, the negative acknowledgement is nothing but sending one bit flag using physical uplink control channel, which is not error protected. That means here we are not adding any CRC or we are not adding any FEC bits when you are sending NAC packet in uplink from handset to the base station. So because of that, if this bit get flipped from let's say 1 to 0, what would the base station think?
The base station will think that everything is fine and it will send the next code
Yeah,
block
exactly.
group.
Exactly. So because of that, what could happen? Even though the handset has not received, base station is thinking otherwise and it is proceeding to transmit other code block groups and other transport blocks. That's the reason why we are saying this point. Hybrid ARQ is not completely reliable because there is no error protection for AX and NAX coming from the receiver to the sender. Is that clear now?
Yes, sir.
And in case if this hybrid ARQ is not able to successfully retransmit all the unsuccessfully received packet, we have to rely on the higher layer. For example, one option is using RLC. If at all, if you want, you can also use a TCP that is separate. But in the context of IG L2 stack, we have this RLC AM mode where when, like look at the, maybe I will explain that with this small illustration at the bottom. So look at case. This is the case where we are sending these RLC packets. These are RLC blocks, okay? So RLC block is the one that we have it in the RLC buffer, and MAC layer will take these RLC blocks and send it as a transport block over the air. That's what happens when you look at RLC and the MAC layer together. But I'm showing this illustration at the RLC layer, not at the MAC layer. In this case, what you see is RLC block 1 or RLC packet 1, 4, 5 have been received successfully. Whereas the block 2 and 3 have not been successfully received. And in this case, we need to get a acknowledgement from the receiver, where the acknowledgement from receiver is carrying a lot of information. In this case, receiver is telling to the transmitter, basically I'm talking about RLC entity here, which is configured in AM mode. Similarly, the RLC entity at the transmitter. So the correspondence is happening between these two entities. After receiving these packets, if the receiver is sending ACK, where it is telling that I have received 1 and 4 successfully, but I couldn't get 2 and 3 successfully. Then the transmitter is going to retransmit 2 and 3. But if you, I don't know whether you remember or not. So did you recall our discussion on how RLC mode, or how RLC works in AM mode, where we'll be sending acknowledgements. So can you recall how we were sending acknowledgements in the context of RLC? There is something very peculiar or specific in the way you send acknowledgements at RLC layer, which is different from the way you do it at the MAC layer. So what is that?
Status PDU, sir.
Yes, you are right. This ACK is nothing but status PDU. You are right. So what you do is you take status PDU and you compose a transport block and you send it to the MAC layer. Then what MAC layer will do? It will use one HARQ process. And each HARQ process is protected using FEC and CRC. Do you understand what I'm trying to say? Since this is nothing but a payload that is coming from RLC layer to the MAC layer, in this case, this payload is the one that is carrying acknowledgement at the RLC layer. So that way the MAC layer, it doesn't distinguish between all this. It takes it as a transport block and give it to one of the hybrid ARQ process. Then depending on how many times you wanted to retransmit, it will try multiple attempts and do that. Of course, even RLC could also go bad. In that case, if it is the transport layer, maybe TCP or other kind of protocol can rely on. Even if those are also not working, application has to figure it out some other way, or ask the application, or application may ask the sender to transmit by using other kind of communication medium. So all that happens at various layers in the protocol stack. Again, yes, Ranjita, what you said is correct. It is status PDU, but do you remember how the status PDUs are actually sent? That means, how do you trigger the status PDUs?
The timer.
Yeah, so there are two cases that we discussed where, like here, after it received block 4, it comes to know that 2 and 3 are not successfully received. So it is setting a timer. If this timer expires, then it can voluntarily send this particular status PDU. That is option number 1. And option number 2, what I was discussing was polling, where the transmitter itself can ask the receiver that, okay, I have sent you multiple packets. Why don't you give me the status update of how many you received and how many you have not received? So in either of these cases, we have the RLC entity at the transmitter getting these ACKs and NACKs at the RLC layer. And where this packet, the dotted line that you see, this is the status PDU, this is protected. Unlike the ACKs and NACKs that are there at the MAC layer. But what is the main difference if you look at between the way you are doing acknowledgements at the MAC layer versus at the transport at the RLC layer is the MAC layer acknowledgements are kind of comes very fast. Where if you recall, like if you look at this discussion, if you look at here, for every transport block, depending on the configuration by the base station, the handset has to give ACK or NAC. It cannot wait leisurely to give ACK and NAC. Depending on what base station says, it gives its so and so time. That's it. It could be ACK or it could be NAC. But that is not the case when you look at the RLC layer. Here, either transmitter has to explicitly ask by doing polling, or the receiver has to voluntarily send whenever the timer is firing. That way, the acknowledgement will come slowly here, and the reliability can be guaranteed, but that reliability is done at a much slower time scale than the things that are done by the MAC layer. That is the main difference between how the MAC layer does the retransmission versus RLC layer is doing the retransmission only in the case of AM mode, not for other two modes. So in summary, so we have discussed about how we can use MAC layer with the hybrid ARQ for fast retransmissions. If you want another level of reliable transmission, you can use AM mode at the RLC layer, which give you the slow and selective retransmission, where you can retransmit only those unsuccessfully received RLC blocks. If you need in-sequence delivery, you can configure it PDCP, which is a kind of thing not there in LTE, because in 5G they wanted to cut down a lot of processing delay and waiting times to support URLC use cases. And also if it comes to the URLC, we can also do something more. For example, sometimes there could not be enough time for you to even to do retransmissions. Even though I'm saying that I have hybrid ARQ, you may configure hybrid ARQ with the number of retries set to only 1 or 2, depending on the application or user. So you cannot set it to, let's say, 10. So if it is like what you can say, non-real-time traffic, like web browsing or file transfer, yes, you can set retry limit to very high. For URLC, you may be setting it to 1 or even 0. If at all, you cannot even wait more than few microseconds. That is one approach. And other approach is using slow modulation scheme like QPSK with a very low coding rate. If you recall, I was showing you about an example where you are packing only 10 bits, 30 bits out of 1024. So where too many number, almost For sending 30 bits, you are almost adding 1,000 parity bits. Look at here, how much amount of the redundancy that you are adding. The idea here is cost will be receiving it, no matter how bad is the channel. So this could be configured for some other applications. Okay, these are some
But it will be, but sir, if we are doing that, it will be very slow, right? Like,
yes, yes.
because first of all, it is QPSK. That is already slow enough. Then we are adding so much of redundancy bits over just 30 bits of actual data.
You are right. You are right. But
Right.
is there any other way? Yes. See, there are two cases. See, ultra reliable, low latency. So there are two cases. Again, you can have some application which require ultra reliability. You can have some application that require ultra low latency.
Okay.
There could be some application which require both of them. In all these cases, one can configure all these parameters. I'm not saying that one should use it. What 3GPP says is that these are all what is available at the disposal of the scheduler, packet scheduler. So one can come up with a different logic in trying to do the trade-off between spectral efficiency and application QoS satisfaction or operator's revenue, whatever it is. Depending on your objective, you would try to play with these parameters.
Right, sir. Right.
And these are some of the references that I have. I think this is the reference for the MAC layer. Which one is that? Yeah, this is for the MAC layer. And these are the two books that I was asking you to go through. And if you have ACM student membership, you can get it. And this is a survey paper on LT, but it also has very good introduction to all sorts of packet scheduling algorithms. The other day I was talking about channel aware, channel unaware, QoS aware, and whatnot. All those are nicely described here, including some comparison reason of some of the scheduling algorithms. And this is also another interesting blog that talks about what is hybrid ARQ, which is a kind of summary of what is there in these two books. So if you don't have access to this book, at least go through this blog.